A very good evening to the students of class 12. We have completed the chapter number 1 and we shall now move to chapter number 2. Now in chapter number 2, what are we exactly going to do? It is also a part of electrostatic. As you can see the name of the chapter, electrostatic potential and capacitance. Okay, so we shall first understand what is the main connection between various topics of this chapter, and then we shall move forward towards the chapter. Now this chapter consists of mainly 3 topics, that is the potential energy, which is electrostatic, potential and capacitance. Let me put it as electrostatic potential energy. Now you may be thinking, from where is this word potential energy coming in electrostatics? For that we have to do a small comparison between gravitational field and electric field. Now you have already learned in standard 9 that the force between two particles or bodies with masses m1 and m2 is given by gm1 m2 upon r square, where g is a gravitational universal gravitational constant, m1 and m2 are the masses of the body which are into consideration, and r is the distance between them. Exactly the same in chapter number 1, we have learned the force between two charges, which was the Coulomb's law. This is the gravitational law. And this is the Coulomb's law, K Q1 Q2 upon R square. Correct? See, we have to learn always with comparison, only then the concept will be understood. So, when we are talking about gravitational law or Coulomb's law, what is the comparison? That here the distance between the masses is r, here the distance between the charges is r. Correct? So, if this masses can have a gravitational potential energy, then these charges also must have electrostatic potential energy. Agree? Okay, the gravitational potential energy given by mgh due to the gravitational field. Similarly, we must have an electrostatic potential energy, whose formula we will derive in this chapter. But at present, let us write it is denoted by U. So, directly potential energy is written in this chapter, but actually it is electrostatic potential energy in the electric field, just like gravitational potential energy in the gravitational field. Agreed? Okay. So, we shall derive the formula of U. Okay. Now, let us go to the next topic, that is the electrostatic potential. What is the electrostatic potential? In this case, there are two charges, correct, Q1 and Q2. For the potential energy, agreed? Here there will be only one charge. What will be the other charge? Will it be there? Yes. But what will be its value? 1 coulomb. Then we will get the electrostatic potential V. That is also energy stored, but by the charge having 1 coulomb. Agree? Now we are saying the energy is stored. Potential energy is stored. That is, the work done is stored in the form of potential energy. Then where is it stored? In a capacitor having a capacitance C. Okay. So I am trying to link up the topics of the chapter where electrostatic potential energy is the work done in the electric field. If the work done is on a unit charge, then it is electrostatic potential, which is also stored. Where is it stored? In a capacitor, whose capacitance is C. So this is the summary or the beginning of this chapter, where we are trying to find out how can we store the energy, the potential energy, the potential. That's all. So now we go to our first derivation. Before that, you just take a screenshot of the comparison and what are they denoted by and the names. Very important is the child does not understand the question itself because these words are new to you. Electrostatic potential energy, electrostatic potential, capacitance. These are new words which you have learned for the first time in your curriculum. Agree? Okay? Or even if it is learned, they have to be remembered now because you are going to use them in the numerical. So understand what I have explained in brief about these topics, and in detail we are going to learn about these topics only in this chapter. Keep watching the video till the end. Fine? I am Dhanu Saraiya and we shall begin with this chapter number 2 of class 12. Before that, just take a screenshot and we shall go to the next topic. Yes, now we shall derive an expression for potential energy. As I said, it is electrostatic potential energy. Electrostatic means it is the energy of a static charge. Okay. Now, as you can see in the diagram, I have placed a positive charge plus Q, which has produced an electric field of its own with some configuration. And I have another charge, again positive plus Q, which is very small compared to the charge plus Q, capital Q. This is the charge which has produced the electric field which is required. That's why it is the source charge. Agreed? And it has a positive configuration. Now, what am I trying to find out? I am trying to find out electrostatic potential energy when I want to bring a positive charge which is small, denoted by Q, small q. I want to bring it from the point R to the point P. Now, as can be seen, both these charges are positive. So, there will be a repulsive force between these two charges. And against the repulsive force, I have to bring the charge plus Q towards P from R. So what I have to do? I have to bring a small charge Q towards a source charge capital Q, which is stationary, Okay, and I have to apply one force which is external against a force which is repulsive due to the electric field between Q and Q, this Q and this Q. Now here I write one negative symbol indicating that both these forces, that is external force which I am using on this charge to bring it towards this charge, and the electric force which is repulsive, are opposite to each other. Agreed? Okay? And one more thing which I have to remember, that this charge must be small so that its own electric field should not disturb the stationary position of this Q. Otherwise, this Q also will move this side or that side. Or it will repel. It won't move towards because it is positive, it will repel. And it will change its position. So these two things have to be kept in mind. The charge Q must be small such that this charge Q remains stationary, and the external force which I am applying on this charge is opposite and equal to the electric force of repulsion between these two charges. Okay, so now what is the net force on this charge? 0. So net force on Q, how much? 0. What is the acceleration? On this charge? Nearly 0. When can I have a 0 acceleration or nearly 0 acceleration? Only if the speed with which I am bringing this charge towards the source charge is constant. So all these points which I have written here are connective and should be remembered, because these are the points which will be asked, or you have to connect it to solve the numerical. These points itself are questions. Here I am bringing the charge with a constant speed with 0 acceleration. Net force on the charge is 0. Why? Because F external is equal to negative of F electrostatic, that is the repulsive force between these two charges. Connect it like a story. Okay? So, the work I have to do in bringing this charge against this repulsive force is given by W, work done, F external I am applying from our knowledge of 11th standard. Work is a dot product of force and displacement, where dr is the smaller displacement here in bringing the charge from R to P. Now let me just take a break here and make you understand some amount of maths. In this some amount of maths, the distance between the two charges can be denoted as R, where I have broken the distance into small parts of dr such that I go very slowly. Okay? That dr I have put here. and this is force into the displacement or force dot displacement, which is the dot product of work, and my maths here is integration. What is integration in maths? Integration is just summation of the small parts. So if this is the small work done in bringing the point from R to P, I am bringing the charge from R to P. If this is the work done, then I have to add it. And how do I show I have added it? I will put an integration symbol. So what is this integration symbol telling me? Summation of F external dot dr displacement. So this is the work done in moving the charge small q from R to P. The integration indicates the work done addition from R to P. Fine. Just now we have seen F external is equal to negative Fe. So I will just write that down. Negative R to P F external Fe dr. Okay. So this shows us that the work done will be stored in the form of potential energy in the charge q. Every point I shift from R to P, there will be a potential energy at every point. That work done in bringing the charge from R to P will be stored in the form of potential energy in the charge. So let us write potential energy difference delta U is equal to UP minus UR, which was or which is the stored work done from R to P. The work which we are doing in shifting the charge is stored in the form of potential energy difference, where UP is the potential energy at the point P, UR is the potential energy at the point R. Where? In the electric field. Agree? So, in the next page, we shall define potential energy difference. Okay? Electrostatic potential energy difference and potential energy. Okay? At a point. With this formula, just take a screenshot of what I have written as a derivation part, and then we shall go to the next page. Okay? So we write the formula again. Delta U is equal to UP minus UR, which is equal to WRP. Okay? And we define potential energy difference as the work to be done to bring a positive charge Q from the point P to the point R, which is stored in the charge Q as potential energy. Agreed? Okay. Now, let us decide from where exactly we can possibly bring the charge towards the source charge. Again, I roughly draw the source charge and the small charge. Both are positive. This is capital Q and this is small q. From where can I bring it? From R to P, correct? What can be this R? This R can be infinity and the point P can be the point P itself. So let me substitute here, instead of R, I can substitute infinity. So that what do I get here then? I get here U P minus U infinity is equal to W infinity P. So now what do I read it as? U infinity is nearly equal to 0. So then what do I get? I get UP is equal to W infinity P. Now can I read it? What is this now? UP is the potential energy at P, which is equal to the work done in bringing the charge Q from, this first it was from R to P, now it is from where to where? From infinity to P. That is the definition of potential energy at a point P. That's why I took a separate page so that you understand the difference between potential energy difference. It is from a point R to a point P. You are shifting the charge from R to P. Then it is potential energy difference. If you are shifting a point from infinity to P, then it is a potential energy at that point of the charge, which is equal to W infinity P. So what is it defined as? It is the potential energy at the point P, which is equal to the work done in bringing a positive charge Q from infinity to that point P. That is potential energy at that point P. I take some other point between P and R, then that will be the potential energy of that particular point. So at every point, a potential energy will be there, and if you find out the difference, it is a potential energy difference. These all words will keep coming, and you have to remember these words. These words are your numericals. Potential energy difference and potential energy. At a point. Agreed? Okay. Now in both the cases, whether it is potential energy difference or only potential energy, the work done which we can see here and here does not follow any path. That means when I am bringing the charge from one point to another point, I need not follow any particular straight path. I can come by any route, because the force which I am applying, the electric force or equal to the external force which I am applying, is conservative force which does not depend on the path followed. It depends, the work done depends only on the initial and the final point. Depends on the initial and the final point. Work done here does not depend on the path followed. Okay? Because the work is done due to the conservative force. It only depends on the initial value and the final value of the work done or the potential energy. Fine? Clear? So now I will just move from here and take a screenshot of what I have taught just now. Okay? Now, from the same concept, let us go to the second part of the chapter, that is, these are introduction, that is simply electrostatic potential. We have introduced electrostatic potential energy. We will now go from here only to electrostatic potential. Okay, now till now we were saying, as seen here, we wanted to bring one charge q of certain value from infinity to the point P or from R to the point P. Now, we want to bring the charge Q is equal to 1 coulomb. So, what is that? Q is equal to a unit charge. So, if we want to bring a unit charge from infinity to the point P, then we name it as electrostatic potential. Okay? Not electrostatic potential energy. When can we say it as electrostatic potential energy? When we are considering Q as some value. But when we consider Q as a unit charge, then we are doing the same process, but we call the value of the potential energy as electrostatic potential. Let us see it. So the work done on a unit positive charge Q to bring it from R to P is given by Vp minus Vr is equal to Up minus Ur divided by Q. Why? Because here Q is equal to 1 coulomb, unit positive charge. Okay? So this we can say it as delta V also, which is Vp minus Vr, where Vp is the potential at P. Similarly, Vr is the electrostatic potential at R. And the difference is potential difference. How much? Delta V, which is equal to Vp minus Vr. which is equal to the work done in shifting the unit positive charge from R to P. Agreed? Okay. Now, if I want to define a potential at that point, this is potential energy difference, potential difference. If I want to define Vp, what is Vp? It is the work done in bringing a unit positive charge Q from where? From infinity to P. Okay, so this is the potential at P is equal to Vp, which is equal to work done in bringing a unit positive charge of 1 coulomb from where? From infinity to P. Agreed? And this is from where to where? From R to P. R to P. This is from where to where? From infinity to P. If I bring it from one point to another point, then it becomes potential difference. If I bring it from infinity to P, then it becomes the potential at that particular point P. Understand all these words. So, we have learned potential energy difference, delta U. Then we have learned the potential energy at that point, UP. Here we have learned potential difference. Okay? And here we have learned potential at the point P. Okay? When the word difference comes, it is from one point to another point. When the word at that point comes, then it is at that point where you are shifting the charge from infinity to that point. Clear? Okay, so all these points you must remember and keep your head cool to understand what are these concepts actually. We are going to derive the formulas for these values also, Vp, Up, everything we are going to derive with respect to charge. We have not done that yet. We will do that. But first of all, understand what is potential energy and potential. Agreed? Potential energy is bringing some charge of some value which is small from one point to another. And what is potential? It is bringing a unit charge of value 1 coulomb from one point to another. That's all. I'll just write it in short. What is potential energy? This has to be understood because students get terribly confused for the question. Potential energy, what are you doing? You are bringing a charge Q from infinity to P. Okay? Or from R to P. What is potential? Only potential if I say, then I am bringing the charge of the value 1 coulomb from where to where? From infinity to P or from R to P. If I say R to P, then it is difference, delta U. If I say here also, then it is difference. But if I say from infinity to P, it is the potential at that point, P point. Okay, this you have to remember. Agreed? Then we will find out the values of UP, VP as we go further in this chapter. Now you take a screenshot of what we have done and understand what I am trying to do and make you understand the concepts. Fine? Okay, I shall move. You take a screenshot.